Welcome to a demo of the TAF Location Service with GNSS tool. Location Service provides the mechanism to register and receive location updates, satellite vehicle information, jammer signals, NMEA, and measurement updates. The positioning service can be used to obtain geolocation and time information from satellite navigation systems. GNSS, or Global Navigation Satellite Subsystem, is a satellite navigation system with global coverage. The application can enable or disable the GNSS device. Currently, the GNSS device is enabled by default for the positioning service. We will start with the Legato GNSS app tools, which depend on the TAF Location Service to demonstrate the usage of Location Service. The GNSS tool contains 3 API files: le_gnss.api, the main APIs for GNSS device control; le_position.api, to access the device's physical position and movement information; le_positioncontrol.api, to enable or disable the positioning service. This diagram shows the GNSS device state machine. A GNSS device has 4 states: uninitialized, ready, disabled, active. The TAF Location Service defines compatible APIs to support each state and maintain the state machine. By default, GNSS is enabled. The device boots up in the uninitialized state. Next, the component init from the TAF Location Service sets the GNSS state to ready. When calling the le_GNSS_disable API, the state is changed to disabled. Similarly, the le_GNSS_enable API sets the GNSS state back to ready. The last state is active. The device must be in the active state to get location, 2D, 3D, or any other information. When you call le_GNSS_start, it will call a TAF GNSS start API in the TAF Location Service, setting GNSS status to active. Similarly, le_GNSS_stop calls TAF GNSS stop in the TAF Location Service, setting the GNSS state back to ready. This diagram shows the design of TAF Location Service. TAF Location Service.adef is an application definition file for TAF Location Service. Inside are 3 API files: TAF_GNSS.api, TAF_position.api, and TAF_positioncontrol.api that correspond to the APIs mentioned earlier. The Legato APIs are provided for the GNSS tool, and we provide compatible TAF_GNSS APIs. When the tool is used, it will call the respective API in the TAF Location Service: TAF_GNSS.api, TAF_position.api, or TAF_positioncontrol API. On this slide, you see the structure details of TAF Location Service. The 3 API files on the left define various API functions. On the right are 2 source files: TAF GNSS implementation and TAF position implementation. The files on the right provide the implementation to the APIs defined in the files on the left. Now we move on to the GNSS tool for testing TAF Location Service, to see how the tool looks and which components are present. This is the GNSS tool source code in component.cdef, the component definition file. Notice the API mappings. le_GNSS calls TAF_GNSS.api. le_position maps to TAF_position.api in the TAF Location Service. le_positioncontrol calls TAF_positioncontrol.api. Below, the source file GNSS.c is named for this GNSS tool application. Let's look at ADEF files. Every application or service must have its own application definition, ADEF file, else it cannot run. Here, tools.adef supports multiple functions. The bindings start at line 26, with the 3 binding samples for GNSS on lines 41, 42, and 43. LE underscore GNSS maps to TAF underscore GNSS. LE underscore position maps to TAF underscore position. LE underscore position control maps to TAF underscore position control. That is how you can build any TeleAF application, provide the bindings, and trigger the TAF location service. You can write your own TeleAF application, defining the components in the same way that the GNSS tool is designed. Next, let's look at the GNSS.c file, which is a source file. In Get GNSS Params, it lists all available options. Firstly, the GetState API, LE underscore GNSS underscore GetState, gets triggered whenever you want to get some information from the TAF location service. After that, you can get features like the time to first fix, TTFF, acquisition rate, ACK rate, leap seconds, and constellation. Next, let's look at how we can run the tools application. Basically, the GNSS tool is part of our TeleAF image. Use sourceset_AF_env.sh SA515M to set the source environment variable on target SA515M. Next, use the command build SA515M-AF to create the TeleAF image. The image file, named teleaf_ro.squashfs, can be found in the directory teleaf build SA515M. Then, you push the teleaf image onto the device to test the GNSS tool. How can you include this application in the teleaf image? In the system definition file SA515M.sdef, this line shows an apps, tools folder under legato_root. This is where the GNSS tool is contained. When you include this in your system definition file, it will be part of the build. Let's connect to the device and run some of the features. At the command prompt, type adb shell. Then type GNSS help for the help menu. Here you see the features supported by the GNSS tool to trigger the various APIs in TAF location services. For example, GNSS Enable and GNSS Start. GNSS Start has options for hot, warm, and cold. GNSS Fix is for looping for certain time for the first position fix. Next are the supported NMEA sentences and supported constellations. When GNSS GET is called, the GET state is the first API to get triggered to start the detailed reporting. Among the parameters are TTFF, acquisition rate, constellation, location 2D, location 3D, time, date, horizontal speed, vertical speed, direction, satellite information, position information, and status. You can see all the available features in TAF Location Service. More features will be updated as service evolves. Here we'll demonstrate some of the features. Type GNSS Get Status for status, which is currently active. By default, the GNSS device state is ready when the device is booted. GNSS Stop returns success, and now GNSS Get Status returns ready. GNSS Enable shows that it's already enabled, so you don't need to do anything. After you run GNSS Disable, GNSS Get Status returns disabled. GNSS Enable returns success. Then GNSS Get Status returns ready. To get location information, the device status needs to be active. Let's try to get the location with GNSS Get Location 2D. That shows that GNSS is not in active state. So we type GNSS Start to run the GNSS engine. Now the status is active. Now GNSS Get Location 2D returns latitude, longitude, and horizontal accuracy. You can see in the source code how exactly this mapping happens in the source file. When you search the GNSS.c file for Get 2D Location, you can find the LE_GNSS_GetLocation API, line 1395, that gets triggered in TAF Location Service. Position sample ref is passed to TAF location service. After receiving the callback function, all the GNSS-related information is filled into the structure of the sample reference. The latitude, longitude, and horizontal accuracy are output parameters. That means the TAF location service returns the information and the tool displays it based on the result that returns from the API. Similarly for altitude, altitude requires location 2D and location 3D. GNSS Get Location 3D returns the 2D information plus altitude and vertical accuracy. In the GNSS.c file, you can see the API le_GNSS_GetAltitude. When it gets triggered, it calls TAF GNSS Get Altitude in the TAF location service with the same input parameters and these two pieces of information as output. It runs a calculation on the results and displays the altitude and vertical accuracy. Similarly, you can run other commands. GNSS Get Time returns the current time. GNSS Get Date returns the current date. GNSS Get TTFF returns the time to first fix. GNSS Get Sat Info returns satellite information, and so on. You can try all available options in the GNSS tool and test all these APIs. Thank you for watching. Please watch the next short video in our TeleAF series, the Car-to-Cloud Photo Demo.